so this whole chapter is on equilibrium. Okay, so how do you know if a reaction is at equilibrium? Okay, you want to check those back and forth arrows. Okay, back and forth. Which means the reaction is not one arrow, but it's an arrow that goes back and forth. It's defined by an equilibrium constant. To what extent it moves forward is defined by the equilibrium constant, okay, which is products over reactants. This is capital K. Okay, and don't forget, whatever product, you raise it to the coefficient, and whatever reactant, you raise it to the coefficient, so you always want to get your equations balanced. Okay. And what do we not put in here? Never put these two things in. Okay, you're not going to put solids or liquids. All right. So very good. So some rules here I'd like for you guys to know. So you see two equilibrium reactions. Okay, if we add them, okay, the equilibrium constant gets multiplied. I'm going to multiply the equilibrium constant. Okay, so right here, when we add reaction 1 with reaction 2, you'll get a new equilibrium constant, which is K1 times K2. Okay? So you add two reactions, the equilibrium constants get multiplied together. Okay, that's rule number 1. So just know these two rules. Okay, what happens when you add two reactions? You don't add the equilibrium constants. What do? Okay, you'll multiply them. All right, let's go to rule 2. Okay, if you multiply a reaction by some number, so let's say I multiply this reaction by 2. I'm going to multiply this reaction by 2. Okay, what will the equilibrium constant become? You do not multiply the equilibrium constant by 2. What do you do instead? Okay, you square it. Okay, so you raise it to the power. Okay, this is rule 2. Okay, so if you multiply a reaction, not adding, okay, you multiply a reaction by some number n. Okay, the new equilibrium constant is raised to the power of n. Okay. If you multiply this reaction by 3, what will the new equilibrium constant be? Okay, you will cube it. If you multiply this reaction by 1/2, you multiply, so the coefficients get multiplied by 1/2. What will this new equilibrium constant be? Okay, you raise it to the 1/2. Okay, you multiply this reaction by 4. What will the new equilibrium constant be? Okay, you will raise it to the 4th power. Okay, you guys see rule number 2? Okay, so what's rule number 1? Add two reactions. What do you do to the equilibrium constant? Multiply both of them together. If you take a reaction and multiply it by some number, you get a new reaction. And what is the new equilibrium constant for that reaction? Okay, raise it to the power. Right, our final rule that I'd like for you guys to know is that when you flip a reaction, what happens to the new equilibrium constant? Reaction becomes flipped. So the new equilibrium constant becomes not negative. You don't change the sign. What do? You take the reciprocal. Okay. So these are 3 rules that I'd like for you guys to know. Okay? They're very different than if you took Chem 1 enthalpy, you add two reactions, you add the enthalpies. Not so here. Add two reactions, you multiply the equilibrium constant. Multiply a reaction by 2, you take that enthalpy and multiply by 2. Okay? Not so for an equilibrium reaction, you raise it to the power. Okay, you flip a reaction, reactants become products, products become reactants. The delta H changes sign. Not so here in an equilibrium reaction. If you flip a reaction, the new equilibrium constant is the reciprocal. Okay, so these are some new rules with regards to K. So here I'm going to write flip a reaction. What do I mean by flip? Okay, reactants now become products, products become reactants. The K, the equilibrium constant is 1 over K. You take the reciprocal. So those are 3 rules I'd like for you guys to know, okay? All right, let's move on to our next page here. Let's move on to page 9 in our notes. Okay, so those are 3 good rules to know for your homework, for your problems. Also a little bit later on in chapter 15, we'll come across this again. All right, now I want to talk to you something that's very, very different, okay? And basically what I'm going to introduce to you now is something called Q. Q is called the reaction quotient. Okay? So basically if you look at the reaction quotient and you look at the equation for the equilibrium that I told you, some products over reactants, okay, they're the same. They're the same. Are they really the same? Okay. The answer is the equations is the same, but the answer is that it's not the same because these are equilibrium concentrations. Okay, these are concentrations that when the reaction settles. Okay, this Q, we do not know if they're equilibrium concentrations or not. So we ask ourselves a question. All right. Okay, use Q when we're asking ourselves this question. Okay. The question is this reaction at equilibrium? And if it is not at equilibrium, and if not, okay, not at equilibrium, okay, which way will the reaction go to establish equilibrium? Okay, which way will the reaction proceed? To get to equilibrium. All right, so are we at equilibrium? And if we are not at equilibrium, which way will the reaction shift to get to equilibrium? Okay. So basically we compare Q to K, and I'm going to teach you something called the Gator rule. Have you heard of this Gator rule, the Gator? Okay, so let's go over the Gator rule right now. But I want you to compare Q to K. That's what we're going to do. Okay. It's the same equation, but we compare. So to do this Gator rule, you're going to have to put Q first. Otherwise, what I'm teaching you is not correct. Okay, so for this Gator rule, put Q first. Okay, that's the caveat. Okay, put Q first. Okay, as we put Q first, okay, there's 3 things can happen when you compare Q to K. 1, Q equals K. Okay, put Q first now. Q is greater than K, and Q is less than K. All right, so for this Gator rule, I'm going to call it Gator rule. Okay, put Q first. If Q is greater than K, okay, where do the gator jaws point to? The reactant side or the product side? Okay, where is the gator chomping? Reactants or products? Okay, reactants. So the reaction is not at equilibrium. Which way will it go to get to equilibrium? Reactants. Okay, so we're not at equilibrium, but to get to equilibrium, where will the reaction shift? Reactants. Okay, so we're not at equilibrium concentration, so it's going to shift to the reactant side. Okay, to get to equilibrium. Okay. If Q equals K, are we at equilibrium? Okay. These are equilibrium concentrations, so we are at equilibrium. Okay, finally, if Q is less than K, where do the alligator jaws point? Where do the gators point to? Reactant side or product side? So are we at equilibrium? No, we're not at equilibrium. Which way will the reaction go to get to equilibrium? To the product side. Okay, where's the gators going? Where's the gator chomping? Okay, so we're not at equilibrium. Not at equilibrium concentrations. Okay, but to get to equilibrium, what do we need to do? You said it, Asia, and you need to shift to products. Okay, then you are established at equilibrium. Right? Okay, so for this gator rule, if you're going to use this gator rule, you have to put Q first. Otherwise, everything will be not wrong. Okay, it'll be flipped. The answer will be wrong. Right? So put Q first if you want to do the gator rule. Otherwise, you can use the textbook, and then the textbook has their own version. Okay, or your ebook has their own version of this rule. But if you're going to use gator rule, what you're going to put first, Q or K? What goes first when you're comparing Q or K? Okay, you're going to put Q first. Okay, it's the exact same equation. Everything is the same, but we want to know, are we at equilibrium? Okay, if we're at equilibrium, good. But if we're not at equilibrium, which way do we go to get to equilibrium? All right, so this is different from the textbook, but okay, remember, I'll add another reminder here. Gator rule, put Q first. Okay, then compare to K. All right, so example of this problem. The Kc for the following reaction is 6.5 times 10 to the 4 at 35 degrees. So notice it's a specific temperature. You change the temperature, you change this equilibrium constant. And in a certain experiment, 0.02 moles of NO, 0.0083 moles of Cl2, and 6.7 moles of NaCl are mixed in a 2-liter flask. In which direction will the system proceed to reach equilibrium? Okay, which way will the reaction go to get to equilibrium? Is this an equilibrium reaction? Okay. Definitely are at equilibrium. It favors the products. Okay, at equilibrium. Okay, when this reaction is complete, we'll have more products than reactants. However, we do not know under these concentrations which way the reaction is going to proceed, okay, to get to equilibrium. Okay, which way will the reaction proceed to get to equilibrium, to get this equilibrium constant at this temperature? All right, so first things first, let's do the Kc. C stands for concentration. So it's going to be NaCl. Okay, we should raise it to what power? Okay, divided by NO. Okay, we should raise it to what power? 2. Cl2, we should raise it to what power? 1. Okay, this is balanced, right? 2 and 2 and 2. It's balanced, okay? Right, so these are concentrations. What we have here is moles and liters. So to get the concentrations, we need moles over liters. So let's figure out the concentrations of each of these guys. So the concentration of NaCl is 6.7 divided by 2 liters. Okay, moles over liter. And I'll just go ahead and get these calculations out of the way. Okay, 3.35 big M. Cl2 is 0.0083 divided by 2. That's 0.00415 big M, moles over liter. And then we have NO is 0.020 moles divided by 2 liters, and this is 0.010 big M. Right, so now we'll plug it into our equilibrium expression. Okay, so plug into equilibrium. Right, the equilibrium expression is right here. So we'll do that. 3.35 squared divided by NO squared, 0.010 squared, times, in the denominator, 0.00415. Okay. So if this is equal to our 6.5 times 10 to the 4th, then we're good, we're at equilibrium. If it does not equal it, then we're not at equilibrium. So what is this equal to? Anybody get this answer? So doing this on my calculator, I am getting an answer of 2.70 times 10 to the 7th. So are we at equilibrium? Okay, so plugging these concentrations into its equilibrium expression, okay, we are not at equilibrium. Okay, not. Okay. So if we were at equilibrium, what would this equal? 6.5 times 10 to the 4th. Okay, but we're not at equilibrium, so which way do we have to go to get to equilibrium? Okay, we're going to put Q first. Okay, we compare Q to K. Okay, put Q first. So what is our Q? 2.70 times 10 to the 7th. What is our K? The K is given to us at the beginning of the problem. 6.5 times 10 to the 4th. So which is bigger? Okay, 10 to the 7th is bigger than 10 to the 4th. Okay, by putting Q first, by putting Q first and comparing it to K, we see, where do the alligator jaws point to? Reactant. So we're not at equilibrium because it doesn't equal to the equilibrium constant. Where will it go to get to equilibrium? Okay, it will go to which side? Okay, it will shift to the reactant side. Very good. Okay, so that's how you do this Q problem. It will shift to the reactant side. Okay, so this is how you do these Q problems. All right, it's called the reaction quotient. Right, I'll cover that again as we do our test review a little bit later on. Another new thing here is something called the ICE table. This is page 11, and nobody likes these ICE tables, but we'll go ahead and do them. Okay. so here we're going to construct a table, okay, and this table is called an ice table. Ice table. So an ice table stands for, the I stands for initial, the C stands for change, and then the E stands for final equilibrium concentrations. Okay, so we'll construct an ice table to get the final concentrations at equilibrium. Okay, that's what we want. Okay, ice table, initial, change, and equilibrium. So the first thing, we'll set it up, and then we'll figure out the final concentrations at equilibrium. Let's do an example. So something like this will be on the exam. The next problem will not be on the exam. The math will not be on the exam. The next problem, the quadratic, will not be on the exam, but this type of math will be on the exam. Okay, the next problem, the math will not be on the exam. That is to say, no quadratic equation. All right, let's worry about this problem first. All right, starting with initial concentration of 0.040 molar HI. Okay, what is the equilibrium concentration of HI, H2, and I2 at equilibrium? Okay, at equilibrium. So here's our reaction. And the equilibrium constant for this reaction, I'll give this to you, so it's going to be 54.3. Okay, and I got it at 430 degrees C. So, okay. All right. So the equilibrium constant for this reaction, which is H2 plus I2, goes to 2HI. This is our equilibrium reaction. We want to find the final equilibrium concentrations when we're starting off with 0.040 big M. Yeah, I got it. Okay, so initially at 0.040 molar HI. Okay. So the first thing we want to do, this is our equilibrium reaction. This is our equilibrium constant, which you'll be given on any exam. You'll set up your table like this, I, C, E. Okay? I, C, E. Okay, initially we have 0.040 molar HI. Initially, we have 0 and 0, H2 and I2. Okay? So which way will the reaction shift? Okay? In an equilibrium, it never goes to 100% completion. You must have some reactants with some products. So initially, you have this HI. Okay? So where will the reaction go? To the right or left? So initially you have 0.040 molar HI. Initially you have 0 and 0, so the reaction is going to shift to the left, okay, to get some of the reactants. Okay, so the reaction is going to shift to the left. You cannot have 0 in an equilibrium. Okay, so the reaction is going to shift to the left. Do you know why it shifts to the left? Okay, so initially you're starting out with this, and some of this reaction is going to go this way. Some of it's going to go this way, okay? You can't go this way because you don't have anything here. Okay? So initially it's going to go, initially you have this in the reaction vessel. It's in equilibrium, so some of it's going to go this way. So the reaction is going to shift to the left to give you some H2 and I2. Okay, that's initially. Okay, so the reaction is going to shift left. It's going to shift left by some amount. Okay, and this amount is not going to be minus X. Okay. Okay, but it's going to be how much? There's two of these. So it's going to be minus 2x. Okay, this will be plus how much? There's 1 mole of it, so it's going to be plus, is it going to be plus 2x? It'll just be plus x. Okay, what about this H2? Is it going to be plus 2x or 3x? Okay, it's balanced. It's going to be plus x. Okay, so finally, this is what we're interested in, is the equilibrium concentration. So we set up the ice table. Okay, initial change, okay, minus 2x plus x, and then finally our equilibrium concentrations, where they are settled. At equilibrium, this will be x, this will be x, this will be 0.040 minus 2x. Okay, why is there minus 2x here? Look at the coefficient. It shifts left, that's correct, Allison, but why isn't it? Why is it not minus x? Why is it minus 2x? Okay, the reason why it's minus 2x is that you have 2hi. Okay? 2. All right, so step 2 here is that we will plug it into the equilibrium expression. This is step 2. So what is the equilibrium expression here? Concentration of Hi raised to the power of 2 divided by the concentration of H2 times, in the denominator, concentration of I2. Okay, let's plug these values in here. So concentration of Hi at equilibrium is 0.040 minus 2x squared divided by, this is going to be x, and that's going to be x. Okay. What's x times x? X times x is x squared. Okay. I'll just write x squared. Okay, this has to equal our equilibrium constant, which is 54.3. All right, so our next goal here is to solve for x. Okay. Okay, step 3 in our ice table is to solve for x. So you'll do this on the exam, just like this. Okay. So we have 0.040 minus 2x squared divided by x squared equals 54.3. Okay, how will I isolate x, or how will I, solve for x? Okay, here you see the square here and the square here. I'm going to take the square root of both sides of the equation. Okay, so take square root of both sides. And if I take the square root of 0.040 minus 2x divided by x squared, if I take the square root, this is what you'll do. You take the square root of this, the squares and squares cancel. So actually this becomes 0.040 minus 2x divided by x. And what's the square root of 54.3? Okay, on my calculator I'm getting 7.369. Okay. All right. Do we know how to solve for x now? Okay, so this is just math, not chemistry. 0.040 minus 2x equals 7.369x. This is math, okay? Algebra. Okay, the minus 2x goes to the other side. 7.369x plus 2x is 9.369x equals 0.040. And then x is going to equal to 0.040 divided by 9.369. All right, I'm getting on my calculator when I do that, and you want to put the units here. 0.0043 big M. Okay, just double check my math. Okay, here you want to put the units, otherwise we'll take off points. The units are molarity. And is this our answer? Okay. Well, that's x, but what does x symbolize? X is the concentration of H2 at equilibrium. What else is also x? The concentration of what at equilibrium? I2. And 0.040 minus 2x is the concentration of HI at equilibrium. Okay? So we plug it back in. We plug this x back in here, we plug the x back in here, and we plug the x back in here, and this will be our answer. Okay? So our final answer on an exam, you want to write something like this. Okay, at equilibrium, H2 will be what concentration? H2 is x. And we just found that x to be 0.0043 molar. Okay, I2 is x. What did we find that concentration of I2 to be? 0.0043 molar. And then HI. What is HI's concentration at equilibrium? Okay, it's going to be 0.040 minus 2x. And that is, if my calculator is right, 0.0314 big M. So this is our answer. Okay. So on an exam, you can do this, but you also have a way of checking your answer. How do you know your answer is correct? How would you know if your answer is correct? What can you do to these concentrations? Okay, you can plug it back here, and what should they equal to? 54.3. Okay, so we'll check our answer. Okay, check our answer. Okay, so we'll check our answer by plugging back into the equilibrium expression. Okay, so this is a nice way to know whether the answer is correct. It should equal roughly about 54.3 or so. So HI, so K is equal to HI squared. HI was 0.0314 squared divided by H2, which is 0.0043, and I2, what's I2 is also 0.0043. And when I did that, I got 53.3, so that's close enough for me. Okay. So check your answer always to see if it sort of matches the equilibrium constant that's given. Okay. So this is something on the exam. Okay. Definitely study this. You're going to take the square root of both sides. You're going to solve for x. You're going to plug it back in and get your final answer, which is this. Okay. If you want to know if your answer is correct, you plug it back in, and it should be about 54.3 or so. Okay, and don't forget the units. Here the units are molarity. Okay, so this is on the exam. Okay, math, everything. Okay, math and how you do it and everything. All right, this next problem is on the exam except for the quadratic. So do you know the quadratic equation? Okay, how many of you know the quadratic? No? Okay, good. It's not on the exam. But let's go ahead and do this anyways. Wait a second. Where's my notes? We'll just take a piece of paper and do it here. Okay. All right, like I said before, this is a problem that will halfway be on the exam. The math won't be because the math is a little bit more extensive, and so we'll just go over it together and I'll tell you what part that you should know. All right, so we have this reaction here, Br2 gas, according to page 12 of our notes. Okay, this is at equilibrium with Br, 2Br, okay? And they tell you that this is 1.1 times 10 to the minus 3. Okay, this is the Kc. Temperature here is 1280 degrees, okay? We quote the equilibrium constant at a very specific temperature. All right, initial concentrations of Br2, I'll put that I as initial, it's not equilibrium, okay? It's initial. Initial is 6.3 times 10 to the minus 2. And the initial concentration of Br, it's initial, not equilibrium, okay? 1.2 times 10 to the minus 2. Okay, so what is the concentration at equilibrium? Okay, so what are the equilibrium concentrations? Okay, so this reaction is going to move back and forth until it settles at the equilibrium concentration, and it's going to settle where the equilibrium concentration, where Br, products over reactants, it's going to equal to 1.1 times 10 to the minus 3. Okay. All right, let's plug in these concentrations here and see if these initial concentrations, initial, is indeed the equilibrium concentrations. Okay. So Br2, products over reactants. So Br is 1.2 times 10 to the minus 2. 1.2 times 10 to the minus 2 is 0.012, okay, squared, divided by Br2, products over reactants, and that's 0.063. Okay, so what does that equal to? Okay, so we're plugging in the concentrations given to us in the problem on page 12. And I am getting, when I plug this in, 0.012 divided by squared divided by 0.063. What do you get? I'm getting about 2.3 times 10 to the minus 3. So they do not equal to one another. So we are not at equilibrium. Okay, which way will this go to get to equilibrium? All right, I'm going to call this Q. and I'm going to call this K. So which is bigger? Q. So which way will this go to get to equilibrium? Reactant side. Okay, so this is going to shift to the reactant side to get to equilibrium. All right, so now we will construct our ice table. Okay, shift reactant side by Gator rule. Okay, by Gator. Okay, so now let's construct our ice table. Br2 gas goes to 2Br gas. Okay. Remember, the ice table is initial, change, and equilibrium. Okay, our initial concentration of Br2 was 0.063. And our initial concentration of Br was 0.012. Remember, it shifted to the left. It shifted to the reactant side. Okay, that's where the Gator jaws point. So this is going to be minus how much x? Minus how many x's? 2x, and this is going to be how much? Plus what? Plus x. So 0.063 plus x, 0.012 minus 2x. Okay. So now we plug it into the equilibrium expression. Okay, which is Br squared divided by Br2. Okay, so what's Br? It's 0.012 minus 2x squared divided by Br2. Br2 is 0.063 plus x. Okay, this must equal to what? Okay, equilibrium concentrations must equal to the equilibrium constant, which is given to us in the problem as 1.1 times 10 to the minus 3. All right, so here onward is not on the exam because here you have to use the quadratic. Yeah?
Only plus x on the reactant side instead of plus 2x.
This is just one.
Oh, okay.
This is 2, Michael, because it's 2 moles. So, yeah, good question. Okay. All right, so here we have to solve for x. And I'm not going to do that math because here you have to get it to the quadratic equation. You know the quadratic? You have to get it into form ax squared plus bx plus c. And this will not be on the test. Okay, so what will be on the test would be from here to here. Okay, but the math will not be on the test. Okay, so quadratic equation. And I went ahead and did all that quadratic equation stuff. And if you want, you can do the quadratic, but it's not on the test. Okay, and I'm getting a final answer here of, to get to answer, let me clarify my comments. To get to this answer, you need to use the quadratic equation, but it will not be on the exam. Okay, so I'll skip a bunch of steps and I'll get you the answer. For Br2, we got 0.065 big M. And then for Br, we got about 0.0084. Okay. But the quadratic is not on the exam. Okay, so just if you want to see the quadratic, it's okay, so I simplified it. I got it. Again, you don't need to know this for the exam. I got it into the form that can fit into the quadratic equation, which is right here. Okay, here's the quadratic equation. I got it into this form. I plugged it in. You reject a couple of options because they give negative numbers. And then, yeah, okay. So that's the quadratic. If you know the quadratic and want to answer it, just verify that you got 0.065 and 0.0084. All right, so on this, again, I just want to reiterate, up to here will be on the test material that you should know for the test. As far as math is concerned, you go to the previous problem. The previous problem will be on the test. All right. Any questions? All right, so don't worry about the quadratic. Don't worry about those steps. The previous problem, where is that previous problem here? I'm losing everything, just like my mind. Okay, this will be more akin to what you'll have to do. You know, take the square root of both sides, solve for x, plug it back in, all that. Okay. So I put some stars here, just so you know.